right. Okay, folks. Thank you for bearing with us, and thank you for bearing with the camera situation and my mask situation. This is a long presentation, and like most presentations I've done of this size, I scrambled to finish it at the last minute. So there's some things that are going to be missing, but we can probably fill those in with discussion. You know, I want to take this in a very relaxed way. But anyway, here we go. So this is a field guide to distributed systems for Elixirists. And there's a reason I called this the field guide. There's no way in this meetup presentation that I'm going to cover a sufficient amount of the theoretical knowledge of distributed systems. It's a deep and active field with lots to read. So if you came to this talk expecting a nuanced discussion of the CAP theorem or Paxos or the FLP impossibility result, if we're going deep, this talk is not for you. Instead, we're going to talk mostly about practical techniques you should know and employ in your Elixir applications. And hopefully this is not too much preaching to the choir. There's a blog post from 2014 that always inspires me from Jeff Hodges, who previously worked at Twitter, called Distributed Systems for Young Bloods. None of us in this room are young bloods. So you're probably gonna go, yeah, Sean, I've done this my entire career, move on. If that's the case, let's do that. So anyway, field guide, just like identifying birds, this guide is about pattern recognition, but so many decisions in your day-to-day are going to be a whole lot of it depends. So these things are just the pen and the paper and the outlines. You have to draw the rest of the owl, so to speak. It's up to you to decide whether the asshole is me because I'm giving this long ass presentation or the distributed system. So let's try to find out. Okay, so why do we care about distributed systems? Why are we doing the distributed systems with Elixir? What is it all about? There are a lot of hard facts that I want to share here. First one is that your Elixir application probably already exists in a distributed system. There's a whole world of things that use the network in a typical web application or API that we don't regularly see or think about. You know, easy one is, does your application use a database? Does it use a third-party API or software as a service? Does it accept client requests over the network? Congratulations, you've got a distributed system. Now you've got N problems. Now, if we wanted to be really reductive, we could argue that multi-core processor in your laptop and all the chips on the main board comprise a distributed system. However, its constraints are really different, so I'm going to kind of ignore that and focus on applications that communicate over some kind of network external to a single computer. Fact two, hard fact, distributed systems fail a lot. Even when things seem to be operating sufficiently well, there's probably one component that is slow or buggy or is about ready to fill up its disk with log files. So if we're going to work in distributed systems, we have to be ready to deal with failure. We can't just write the happy path and expect things to work. Errors are now part of the new normal. So one way that Joe Armstrong has put it, and this might also be attributed to Leslie Lamport, I'm not sure, but a distributed system is one where the failure of another computer can make my computer unusable. And I always enjoyed when Joe would say that. Rest in peace. Another way to put it is by an old colleague of mine, Justin Sheehy. Distributed systems are in a constant state of partial failure. So they may seem to work, but there's something broken. And maybe this fact three, this perception isn't as prevalent nowadays, but it was hyped in a big way when I picked up Erlang about 14 years ago. They're perceived as easy in Elixir and Erlang. Now, having tried way too much in this space, I'd say that some things are easier because you're not fighting your language runtime's concurrency model in addition to the network. But there's nothing that you really get for free by choosing Elixir. One speaker back in the day said that, and this was about Erlang, he said, Erlang makes the impossible easy and the easy possible. And finally, fact number four, hard fact number four, things I'm going to talk about tonight are very contextual. There's no silver bullet. You might find yourself taking a handful of these techniques, applying them successfully once, and then applying them again in a different situation and find they don't work out. All this becomes about developing an intuition, about balancing the guarantees and the benefits you want against the inevitable risks that come with failure in a distributed system. Oftentimes, you may find that doing something that is generally positive will make situations worse. So keep an eye out. Now, even though I promised this wouldn't be theoretical, I need to cover a few concepts just so we make sure we're on the same page, because I'm going to use them probably sometimes extemporaneously, but there are some points where I bring them up directly. So I hope you have some knowledge of these already, because I'm not going to go too deep. The first two concepts called safety and liveness. So theoretical concept. Safety and liveness are classes of properties we want our distributed systems to have. So they have theoretical definitions related to the sequence of states the system takes, and whether those prefixes or suffixes of states cause the property to be violated. It's basically a way to say, here's something positive I want. Can you prove that it will or will not be violated? So they usually come in pairs, one safety and one liveness, but sometimes there are more than two. Every distributed system basically must have one of each to be useful. And I'll go into that a little bit with when we talk about what they each mean. So safety means colloquially that nothing bad happens. It's about preserving step-by-step correctness. So any behavior or sequence of states satisfies the safety property if all prefixes of that behavior satisfy it. So in other words, nowhere in the past, including the current moment, was the property violated. So safety encompasses things like, for example, integrity, data integrity, isolation, so things happen independently, and sequential consistency that you might expect out of your database. Are we still there, Zoom? Can you still see the screen? Okay.
Yep.
We had a little HDMI blip. Okay. Liveness. Liveness colloquially means that something good eventually happens. It's about always making progress. So any behavior that satisfies this liveness property, it will satisfy the liveness property if all suffixes of that behavior can be extended to satisfy the property. So in other words, think about things like deadlock freedom. So you never get into a spot where you can't make progress. Fairness, everybody gets a chance to do something. Or eventual consistency. If you keep trying forever, eventually they will agree. So basically liveness, if you're prevented from making progress, the property is violated. So these are ways to kind of think about, well, what if I apply this technique? What kind of safety guarantees will give me? What kind of liveness guarantees will give me? So remember when I said that distributed systems fail all the time? The outcomes of that can be measured on two axes, harvest and yield, which were coined by Eric Brewer and Armando Fox in 1999. So there's this quote from the paper. We assume that clients make queries to servers, and in which case there are at least two metrics for correct behavior: yield, which is the probability of completing a request, and harvest, which measures the fraction of the data reflected in the response, that is, the completeness of the answer to the query. So yield you may already be familiar with. It's most often framed in terms of nines of availability or uptime. So basically, does this thing return a response, or how often? And harvest is a little bit harder to understand, except for when you're talking about replicated systems, where or systems that have a fan out, fan in type of request style, where you need to query multiple different services to gather a response. And you may want to say that, like one of them, well, it didn't succeed, but I still needed to return a response to keep my yield up. You might say that, well, that's a case of reduced harvest. So I think this is a useful way to frame the guarantees of your system. Like, what are you willing to sacrifice when things go wrong? Do you want to stop responding to requests that can't be satisfied, or do you want to respond with incomplete results? And then finally, Little's Law. Thanks to our friend, Jeff Utter, who unfortunately is not here tonight. But he presented last year. You probably already know this, thanks to him. If you don't, you can learn it now. It directly relates to queuing, which we'll talk more about later. The equation means, from left to right, that on average, the number of items in a queue or being worked on, which is represented by L, is equal to the average rate of arrival, lambda, multiplied by the average service time, W. So service time meaning how long does it take to traverse the queue and get processed. Now, Jeff showed last year how looking at the metrics of queries in his application let him size his database connection pool correctly. So like how many queries were going on, how quickly did they complete, and then how many connections do I need as a result of simple multiplication of those metrics. And it's the law. Let's talk about the techniques. And like I said, I wanted this to be practical. Unfortunately, not on all of these do I have code samples, but on a bunch of them I do. So hopefully you'll be able to read them in the back. Okay, so I feel like I shouldn't have to bring this up, especially amongst this crowd, all these experienced faces. But if you don't have instrumentation in your application, we can't even begin to talk about anything else. You should be logging important events, measuring and aggregating statistics, and like wrapping activities and tracing spans and propagating trace context across the infrastructure. These are all essential in gathering the information you need to make good decisions about what other techniques to apply. Now, the easiest way to get started is with the telemetry library, which many of you probably know. Even if you don't know how you want to collect things, you can start adding calls to this telemetry execute in important spots of your application. And then you can go in later and say, well, I actually need to collect some metrics there or log something and attach it later. So in this case, I have a simple call to telemetry execute. It says, I have this event, which I'm calling job finish. And it has a duration, which I collected from doing the job, and the name. And so we can use that to collect metrics and classify those metrics on important dimensions. So, so once you know what you want to start measuring, you go and you add attach handlers to the event after startup. So when a telemetry execute is called, all registered handler functions will be called, and you can log, record metrics, or create trace spans. In this example, I've decided to log a message and record the duration of the job into a Prometheus histogram and increment a counter. Now, I've done this very manually. So sorry, there's a little bit that's clipped off on the right there. But basically, you attach a handler, you give it a name, and you attach it to the event that it's going to receive, and you pass a function. And then that gets registered for the entire life of your application. And it gets called whenever that execute that we saw on the previous slide is called. So again, I said I've done this very manually. There are more modern ways to achieve the same thing, including libraries like telemetry metrics, which kind of give you a model that can work across different metric systems. And sometimes they give you macros that you can put around your functions to basically count how many times they're called and stuff like that. So I would definitely suggest checking those out. And one further example from telemetry, oftentimes you'll be doing something whose timing you don't want to measure manually, like it's not measured by something external to your code. And you'd like to automatically record exceptions when they happen. So telemetry span lets you do this. And it has nice integrations available with OpenTelemetry tracing and telemetry metrics and so forth. So in this case, instead of calling the handler with the event sequence given, so where it says search index update, it's going to be called with a suffix that is either start, stop, or exception, depending on what phase of the span you're in. And it's just going to add that to the end of the list. So, in the last couple episodes of Elixir Outlaws, Amos and I have been talking about, well, I need to, populate my search index after I've imported my employee list. And I'm like, well, how do you measure that? So I made up this example of, well, I need to measure, how long does it take to update the search index? The other interesting thing to note here is that your inner function you're passing to telemetry span, it needs to return a two-tuple. One is the result that should be returned from telemetry span. And the second is the metadata about the internals of that. So like if it didn't throw an exception and you wanted to pull some things out of that result that's being returned from our pipeline here, you could put it in there, and then the stop callback will get that extra metadata. Okay, so now we've got our app instrumented, we hope. Let's talk about the most ubiquitous technique first, which is timeouts. And again, I feel like I'm preaching to the choir in this room, but the idea behind timeouts is generally that you put an upper bound on how long you want to wait for something to complete. So why would you do this? Well, sometimes things take a long time because they're not operating correctly, or the thing you're making a request to is bogged down with too much work. So by adding a timeout, we're preserving liveness. There's liveness. We're not waiting forever for the thing to complete. One of the saddest truths in distributed systems is that recognizing that slow and not working are basically indistinguishable across the network, right? So timeouts are a compromise that let you draw a line in a place that is reasonable for you, and you can decide past that line, that thing is effectively unavailable, and I don't think it's working. So you'll find that timeouts are all over the place in Elixir and Erlang code, and this is by necessity. If you think about the model of the beam, if your process is waiting on a message that will never arrive, it goes to sleep. And it isn't scheduled to run again, ever, if that message never arrives. Now, adding an after block in your receive makes sure that it can take action again when the timeout expires. So you'll find this all over the network stack, all over OTP, and a ton of third-party hex packages. I think like timeout has got to be the most common additional optional argument in the entirety of all Elixir and Erlang code. And then deadlines you may be less familiar with, but except for maybe Jason. Deadlines are just timeouts, but they're for entire workflows or request trees, and not single calls. So imagine that somebody hits your Elixir apps API over the network and needs a response in a short amount of time. So in processing that request, your app has to call 3 other services and possibly its own database. Now, if any of those other components are slow, you probably won't meet the client timeout, even if you're requesting them concurrently. Now, if you propagate that deadline through your infrastructure, this is usually like some kind of protocol metadata, like an HTTP header, you can ensure that your systems aren't busy doing work, sitting around doing work for a client that has already given up and is no longer waiting. So deadlines are really useful in that like multi-system, multi-service architecture. Okay, so timeouts are insanely easy to implement. So if your request is some message to another process, and after which you try to receive the response as a regular message, you can use the after block to set a timeout and then the action to take when it expires. So this is very similar to how gen server call works when you have a gen server. I'm using makeref because that is a slight optimization in the receive. In the Erlang compiler, it will make a special case for makeref followed by some receive that has the ref matched in the same function. So like I make request, I give it the token, and then when I receive that back, then I'll do something with the result. But if it doesn't complete in 500 milliseconds, then I'm going to abort. I'm going to exit my process with a timeout. Now, if the thing that you need to be time-bound by the timeout is not handled by a shared process, you can spawn a task to take on the work and then limit how long you wait for it to complete. In this example, using task async, which actually does link to the current process. So if that fails, it will crash the current process. But when you pass a timeout to task yield given the task that was returned from calling async, and if that times out, it will return null or nil. And then if it timed out, it'll try to shut down that task. So you're never left in a case where you want to move forward, and that task is still running, and then eventually it crashes and takes down your process. You want to make sure that it's shut down cleanly so that it doesn't crash your own process. So if yield returns a result or shutdown, actually you can receive the result during shutdown. If it returns that the result, then I'll just say the result of the expression is that. If we get nil, then I want to return like error timeout. So this is a pretty typical pattern, and you'll probably see this in other libraries that have their own sort of like spawn mechanic for implementing timeouts. Okay, so let's do deadlines. There's this library by our buddy Chris Keithley called Deadline. It's under this organization called Elixir Tonic on GitHub. But like I mentioned before, Deadline is about setting a global timeout for your entire operation. So Deadline puts this timeout into the process dictionary. And then you can ask the Deadline library to watch your process on that deadline. And if it doesn't complete, if it doesn't exit after that timeout, it'll kill your process. So this is nice if you want to farm out the management of tracking those deadlines to a supervisor that is started up by the Deadline app. It'll just kill your process. This is good for like request processes that are taking too long and so forth. And then you can do things like check if the deadline has been reached and stop your work. And then the way you propagate it is generally like you get the context, you stuff it into that other process that you're spawning via closure, and you set it inside that process. So there's a little bit, I don't know if any of you have worked with OpenTelemetry or OpenCensus or any of this, but sometimes you have to like pass the trace context into new processes you spawn. This is a similar problem. And then that last line in this example is that we're waiting on this task that we spawned up to the limit of the deadline. So even if it continues going somehow by accident past the deadline, we won't continue waiting for it beyond there. Okay, so timeouts and deadlines help us control our liveness guarantees and make sure that we don't get stuck. So what can we do to recover when something like hits a timeout or doesn't respond with something that we expect? Well, the easy thing is to retry. This is the most common kind of recovery from a failure that you can detect. Now, a naive generic algorithm for retrying things is shown here in this example. It takes two functions as arguments. One is to do the work, and one is, should I retry this work? And it's pretty straightforward. You call the function, you check if it should be retried based on the result. And if it doesn't, then you try it again. You do a tail recursive loop. Now, this is pretty naive. What's the problem with this? It may never end, for one. I'm sorry? You'll DDoS yourself, yeah. So the typical pairing with retry is exponential backoff. So, maybe we should wait between retries a little time and wait longer if it continues to fail. And like, as I mentioned, let's not retry indefinitely, because you're basically gonna peg your CPU and then whatever else you're calling. So here's a more sophisticated example. Again, tail recursive, but we added two arguments to this function, which is a delay. So that's the base delay. How long do you want to wait if it fails between tries? And then the number of tries that you want to use. And actually, if I had to do this again, I would probably make the first one 0 and then like the default try is 5, and then do subtraction. But basically, it looks very similar, except we've added the process sleep, and we've added multiplication by a factor of 2 on the delay for every time that we have to retry, and then a limit of 5 on the number of times we'll try. So you will see there's a favorite library of mine in Elixir called Tesla, which is an HTTP client wrapper, and it provides something very similar to this. So do check out Tesla. It has really good implementation of this and of timeouts. Okay. So what are the limitations on retry? We already talked about like you don't want to retry indefinitely, but there are additional ones. If you're going to violate some safety guarantee, you don't want to retry. You want to say, I can't move forward because I'm going to violate that thing. So what do I mean by that? That's like if you have some expectation of having something be at most once. It either got there or it didn't. And those are the two situations I want to be able to deal with. Then you don't want to retry it because you may end up via like some slowness on the thing that's receiving your request, may end up sending that twice. Maybe it's still processing the thing. Maybe it didn't give up when you gave up. So you want to be very careful around the safety guarantees there.
So you mean not idempotent.
Right, if it's not idempotent. And I wanted to put idempotence in this presentation, but there's just too much to talk about. So yeah, try to make it idempotent if you can. If you can't, then be careful about retries. Okay, so another thing is that that algorithm I showed you before in the previous slide still has one more problem with it, is that if you have the same delay interval and you have the same number of tries, you can have a tendency for concurrent processes to tend to like go in sync. And this can produce really weird effects on the side of the thing that you're trying to call. They'll tend to like line up or have this like rhythmic pattern. So you need to add jitter to that delay. You need to say like, I'm going to take a random amount, the some percentage of the delay every time, and like add it or subtract it. And make that somewhat randomized so that you're not like having everything happen all at once. And then the other thing is with retries, you have to be really careful about timeouts, especially it's less about, and there's some other things we'll talk about later that retries can be interact very badly with. So you want to decide, is my timeout per retry or is my timeout across all the retries? And you have to make that decision up front. And maybe you have both, perhaps, but you need to be careful about what is the total amount of time I might spend retrying, and does that hit my timeout? Do I want that timeout to hit earlier? So there's all sorts of weird interactions there that you need to consider when doing retries. Okay, so the next one is buffering and queuing. This is a favorite of people who are new to distributed systems. And it's good reason. Buffering and queuing are a way to smooth out differences among different types of work. So especially when the resource that is being guarded by the queue or buffer is flaky or has inconsistent performance, you can kind of smooth that out and hide a lot of faults from people who are sending things to the queue. You know, you'll find buffers and queues exist all over the place, just like timeouts. In fact, it can be kind of treacherous. If you're accepting new connections from clients, there's a queue in the TCP network stack called the accept queue, or the accept buffer. If you're sending a TCP packet over the network, there's buffers for that packet at every hop across the network. And that's not even mentioning the typical things people think of when they jump to talking about queues. They're new to distributed systems. They're like, oh yeah, I can use a message broker like Kafka or Rabbit or whatever. Or I can use a background job processor like I've got Celery, or I've got Oban, which is the thing in Elixir. And there's like Honeydew, and there's all these other like job queue things. But the big thing to take away from buffering and queuing, aside from I can smooth things out and have a more consistent performance for my consumers, is that things go really badly when your buffers or queues are full. You can run out of memory, you can slow things down, and that's just a few of the things that might happen, and that's why you need back pressure. So I don't know if you all remember this skit from I Love Lucy. Back pressure is a principle from fluid dynamics, and it is the idea that there is a force exerted against the direction of flow of fluid through pipes. So similarly, there are forces in our systems exerting pressure against us completing work. Something is slow, it's fully consumed with work, and so forth. So like, just like Lucy and Ethel at the chocolate factory, sometimes there's just too much work to do and coming at you too fast and you're fighting a losing battle. So back pressure lets you tell the source of that work to slow down in one way or another. So the easiest way to apply back pressure is to bound your queues. Again, this is about limiting the work in progress. Little's law. Hey, we came back to Little's law. So in the Beam, you have to be especially careful because process mailboxes are unbounded. That is for very good reasons. I don't think all of those reasons are correct all the time. And I wish you could choose, but you can't. So generally speaking, you have to make a protocol around whether enqueues to your buffer or additions to your buffer are permitted. And deciding how to limit that is important. And the easy way to make back pressure in the Beam is, for example, with gen server call. You can say, I want to use an infinity timeout on my call. And then anybody who's waiting for a response will just sit and wait. And that's a way to tell them, you can't continue to hammer me with things in my queue. You're going to have to wait before you can queue the next thing. So yeah, if that caller that is trying to enqueue something is in the same node, you can make it wait until a slot opens up. That'll just like put it to sleep, like we talked about before. And the nice thing about that is that that process is responsible for handling something like an incoming request on HTTP or like a TCP socket. It can use the things built into the network stack to say, oh, hey, like caller across the network coming in, I can't take any more. And then all of the things in TCP congestion control will trigger, and then it'll be like, okay, I need to back off and stop sending packets because the other side is not receiving them. I didn't get it into the slide. I wish I had, but there's these great flags for the TCP socket options. Active is the flag, and if you say active once, that says that, and you have to set it repeatedly. So you set it as a socket option on the socket, and it'll send you one message containing, some binary data off the socket. And next time you read, it'll send it as a message. And then you have to set active once again to get the next set of things off the socket. So if you're in the middle of doing something and receiving data off the socket and you need to like make sure that that thing on the other side of the network is not hammering you, active once is your friend. There's also a variant of it that is like you give it a number. You say like, I want to receive up to 10 messages off the socket before you go into passive mode. You can still call read to do it passively, but active once is a great way to thread that in between all the other things your process might be doing. Okay, so bounded queues. The next technique is actually shifting the back pressure, the control, to the client side. And this is typically associated with TCP, slow start, or additive increase, multiplicative decrease. So the idea is that you add capacity as things go well. You say, I can do more work, or I can send more requests, or I can put more things in my queue. And then as things fail, you divide capacity. So you're always backing off more than you're increasing as things go well. And it does create this kind of sawtooth pattern in your traffic. But the great idea about this is that if you don't know what your capacity is, you can set up an AIMD policy on the activity that you're doing and go, well, I'm just going to let the system figure out what the capacity is. And then when it starts to look, things start to look dicey, it'll back off automatically. And I don't have to worry about, well, did I get enough connections in my pool or things of that sort. So yeah, the idea is that you're bounding the work in progress on the client side rather than on the server side with AIMD. There's another great Keithley library called Regulator that does this for you. So you could put a limit on how many times you want to, or how speedily you want to be able to call some service, and then inside this inside this block this function you're passing to regulator ask, you can do the work, and then regulator will slow down the return time of that call based on whether it is succeeding or whether it is failing. So in this case, it would have to raise an exception in order to trigger regulators back off. But you can also do it more manually. Say, ask, can I get a token for this to do my work? And then it may say yes or no, and then you can afterwards say, yeah, it succeeded or it failed. So you can sort of split that apart and do it manually. But this is a great example directly from the README. Okay, so and last, in terms of dealing with queues that can overload, the final possibility is load shedding. So you can choose to drop work that you can't complete and tell the caller to slow down. So some examples of this, of dropping the work. So if you've used Ecto and the DB connection pool, what will happen is you can put queries, requests for connections into the queue. And if they sit in that queue for too long, they'll just get dropped. That's when you get that connection timeout. And it's not that things can't continue to be can be queued, but if it's lived too long in the queue, it'll just stop. And then the queue never overfills because things that are taking too long just get dropped. Another way that is very typical in web APIs is if you send 429 too many requests back to your client, you say, hey, I'm too busy. And then you can make decisions in a lot of cases that you're already too busy without actually starting the work by checking your metrics or having some other sort of signal. We'll talk about one in a second. And then there's some interesting libraries they're a little bit on the older side, on the Erlang side. One called DispCount by Fred Aber, and one called SideJob, which is mostly by I only know, why do I forget his name right now? JTuple. But that was part of React, and it was about saying, well, we want to limit how many of these processes can be running at any time. And so, like, if you want to spawn one, you have to ask, can I spawn it? And then it'll give you back a token, similar to the regulator thing. And DispCount is also like this. It gives you very fast responses about, can I do this piece of work based on the limits that I know? And it has sort of another like token bucket type thing. Now, the easy way out on load shedding, I think, is circuit breakers. And the essence of circuit breakers is, Doc, it hurts when I do this. Well, stop doing it, right? And like, I don't know, like Jeremy, if you saw it at Postmates, but Alan and I were deep in circuit breakers when we were at Postmates. That was the big push by the infrastructure team. It's like, if your stuff is broken, you need to put circuit breakers in it so that things don't propagate forever across the network and cause everything to go down. Anyway, the idea is that circuit breakers will keep some global state. The one I'll talk about it puts its state in ETS. I'm sorry, HDMI problems. Folks on Zoom, are you still seeing it?
We've recovered.
Thumbs up, Dan. Okay, cool. And then it'll count the number of failures. So you can either, similar to regulator, you can say, try this thing inside a function, and if it crashes, then blow the circuit breaker a little bit, or try to blow the circuit breaker. You can also go like, hey, is the circuit breaker open? If so, then I'll go ahead and do my work and then record the result afterward. So here's an example that I came up with using the Fuse library by Jesper Lewis Anderson. It's basically when you want to guard something with a circuit breaker, you call Fuse install, and you give it some options. In this case, I'm saying 10 failures in a second is enough to break the circuit and have me fail fast. And then I want a reset period of 2 seconds. So like, you don't want to like completely break and then never come back. So Fuse includes a reset period, which you say, after this amount of time has elapsed, then I'll try again. And then you could do something like this and say, hey, ask, for the value of this fuse, if it's okay. Then I'll continue and I'll call that service that I want to call and return the result. And then so in the else block of this width, we have blown, which is the result if it says, this fuse is not healthy. This circuit breaker is not healthy. And then you can like return immediately. So you're not even calling the service if it has detected too many failures. And then finally, if you got this result that is error, then you want to make sure to melt the fuse. This is telling fuse, hey, this had an error after I executed it, so that counts toward your running budget, and then return the result. Okay, so this actually went a lot faster than I expected, which is good. Thank you all for sitting and listening to this, and I would be happy to discuss a lot of the nuance here since we have another half hour or so.
Okay, so I want to immediately say that I am the young blood in the room. You're
Okay.
not preaching to the choir. I learned at least 3 pages worth of notes on this talk.
Good, good.
I wanted to comment that now I understand a lot more of what Fred was talking about in Erlang and Anger. Like your talk
Good.
helped illuminate some of the ideas about back pressure. I was like, okay, I vaguely understand this, but I've never had to use Erlang and Anger yet, which is why I was reading it. Now I have a better understanding of why you would need those things and what the trade-offs between various solutions are. So that's great. I wanted to comment that Recon itself has effectively a circuit breaker pattern for tracing, where Fred prevents you from tracing everything all at once because that would crash your VM. And so he puts in like, okay, you can only trace 10 calls of this function or 100 calls of this function. Right. Which I think functions the same way as what you were describing for the circuit breaker pattern.
Yeah, I think with the native Erlang tracing facilities, it's super easy to take down your node if you trace too much. And yeah, that's a good point about Recon.
Let me trace every call to spawn.
Yep.
Wait.
Good stuff. Thank you for that feedback.
Okay, go ahead.
You're saying? Do you want to ask, Bruce?
Yeah, I had a question, which was what is actually the difference between load shedding versus circuit breaker? Because those seem very similar.
Circuit breaking is a technique to implement load shedding. I'm sorry, I didn't make that clear. So load shedding is basically the generic idea of I'm going to throw away work when things go badly. So circuit breaking is a way to say I've encountered too many errors. I need to stop doing that. Oh, geez.
Another question that I had.
Are we going to come back? There you go. Go ahead. Go ahead.
Oh, sorry. I can't tell when you turn your head. You mentioned that this was a field guide. Where would I find a more in-depth look at the subject as a novice?
Where to begin? I don't know. Take suggestions from the floor. I'm kind of lost. I gathered a lot of mine through just working with people. And that's probably not the answer you were looking for.
A lot of this comes from like distributed architecture principles.
Yes.
A lot of it. And so you kind of have to go into some of the deeper, like why do we build distributed systems and how do you make a distributed system work? I know that the guy that does the big architecture talk for Elixir, the main guy, starts with C, big long Italian name.
Francesco Cesarini?
Yes.
Yeah.
He's got a lot of stuff on this.
Yeah, he does. Yeah.
So he's got a book that's pretty good on it.
You might want to repeat that for people.
Yeah, were you able to hear that?
I heard Francesco Cicerine. If you could figure out how to spell that and put it in the chat.
Yes, I will.
Is there anything that somebody might call like the distributed architecture Bible? Anything like that? I'm not aware of anything.
There is the Designing Data Intensive.
That is an excellent book. Yes, by Martin
in
Klebman.
my reading list.
Yep.
I keep being referred to that one, so I suspect that it's on my to read now that I'm heading in this direction.
I would also look a little bit farther afield in things like web application performance and scalability, and network engineering. All these things sort of have. Yes. Here we go. Alan has the book.
It needs more reading.
Well, it's a thick one. It's going to take a while.
That's really dog-eared.
So like and there's a lot of blogs out there that just have like little tidbits of the stuff. If you want the more theoretical stuff, I can recommend one called The Paper Trail. The author's handle on Twitter is Henry R. and I can possibly drop some links. The morning paper by Adrian Cockcroft is excellent about reviewing a lot of distributed systems research. And he will kind of draw it back a bit more into a practitioner's perspective, and he provides commentary without like going into the entire detail of what the paper is about. And then, so like theoretical knowledge, obviously there's probably a list of at least 10 papers that cover like the big stuff. You know, I mentioned in the beginning, the cap conjecture and theorem. You know, Leslie Lamport's work is seminal. Okay, so let's go back. The very first thing you should read if you want to read theoretical stuff about distributed systems is a paper from 1977, called Time, Clocks, and Ordering Events in Distributed Systems by Leslie Lamport. And I'll type that in the chat. Because that gives you a basis for understanding so many other papers, and it's probably the most cited paper on the ACM digital library.
Fantastic.
Safety, liveliness.
Yeah.
Is this all steered more towards things which are eventual consistency in the caps?
No. So there is a blog post by Peter Bayless, and I think it's called "Eventual is Not Enough."
Mhm.
And what he's arguing in there, and like I tried to allude to without going into too much depth, is that you need both safety and liveness to have any useful system. So for safety, you could have a trivially safe system that just doesn't answer any requests. It never violates a property because it doesn't do any work, right?
Yeah.
Now you could have a trivially live system which doesn't satisfy any safety property. You could say it could always return the number 42. Well, it's never going to fail. It knows what the answer is, but it doesn't do any useful work. Like there's nothing. So safety and liveness are always taken together. And they have trade-offs between them. You know, if you wanted to go into it, we could talk about, like, we could pick a system and say, like, what are the safety properties and the liveness properties of this system? If you want to suggest something, I'll try to spitball it. No? Okay.
No, it's cool. I was also the thing you mentioned about timeouts. I also wanted to say that it's like one of the most dangerous things you can do is set a timeout too low.
Yes.
And a repeat too high. It's just shockingly dangerous to a distributed system.
Could you all hear Bruce in the back?
Yeah.
Okay.
Yeah,
Yeah,
it's
good.
like you don't understand the unintended consequences of your requests on systems downstream. They're actually trying to fulfill this crazy thing you've asked for over and over again.
You have
Right.
a real life example you want to share?
Oh yeah, plenty of them. The one I'm living through right now, where I've got a VP that insists that timeout should be 2 minutes against a SQL server on queries that probably take 20 or 30. And so it's just what's happening now is you're queuing up multiple huge queries on that SQL server that eventually just take the whole thing down and craters the SQL server.
Yep. And that's an instance of the server not producing the correct kind of back pressure, right? And that's also a testament to, you need the right metrics in there to see if these things are actually completing. And if you're not getting them out of the server, then you got to try to intuit what's going on from the other side. And it's not always successful. Yeah. But 30-minute queries,
Yeah.
like, is this an OLAP database?
Big database, lots of data.
I was more surprised about the 2-minute timeouts.
2-minute timeouts are big. Yeah. You're like,
Oh, yeah, I do backend systems.
I know, but like Jason and I have done, like you're still at Bleacher Report, right? Like their timeouts are like, what, 500 milliseconds or less?
I mean, the biggest queries we run probably 15 seconds.
15 seconds. Okay. Yeah.
Yeah.
So like total different scale of
Like,
operations
regular
there.
things have to be responsive to users. Yeah, you want
Yeah.
those kind of timeouts, but this is like backend system run, big batch jobs.
Okay.
Lots and lots of queries, lots and lots of stuff are going in there. A lot of IO.
Somebody needs to run a you know, a query plan on those and see why
Oh,
they're
yeah,
taking so
no,
long.
I've definitely personally worked with like stacks of views on views on views that end
Mhm.
up just taking entirely minutes, mostly because none of them have indexes. So it's just
Oh,
like
yep.
trying to compute in real time all the way down this stack of views. And like, can I just have access to the raw data, please?
Yep.
I wish I could.
I like how you said that, timeouts are not errors, which I think
Yeah.
is like, that's,
Doing them dead wrong.
I don't know, from a very naive perspective, like, yeah, you get a timeout, you go like, oh, something's broken, give up, throw in it,
Right.
raise the flag or whatever, but yeah, like, that's more like your signal, right?
Right.
just for
It's a
implementing
signal. Yeah. And I think that when, especially when in my last job and some other ones where we've interviewed back-end candidates, and like we have sort of question about like what might be an indication that something is going wrong, and we're like, of course they say a timeout right away, and they're like, yeah, and so then I'll handle the timeout error, and I'm like, why does the timeout exist? All right, like let's think a little deeper, and it actually took me a while to recognize that they're not an error you handle, they're a tool that you employ. And that means that like actual responses you get that aren't timeouts, whether they're some kind of failure from the network stack or whether there's some kind of like protocol level failure, like an HTTP has all these 3, 4, 500 section things that you might want to consider as not successful or exceptional conditions. Then like you have to make decisions about does this type of unexpected result mean that I should retry, for example, or that I should trigger my circuit breaker? And there's all sorts of nuance in that space. But timeouts are like, no, that's something that you said you wanted to do, either like implicitly or explicitly based on whatever tool you're using. But like that's something that gives you the opportunity to make a decision about something that may not be working. And yeah, it's I think I like that framing a lot better than what I understood when I was much younger. Because I too thought of them as errors. Oh, this is an error I have to deal with. No, it's actually like something that's helping me.
Well, to be fair, for the most part, you don't pick your timeout. I mean,
A lot of
oddly
times you
enough,
don't.
I was going to say, oddly enough, 90% of the time when you hit it, you didn't pick it. Something
Mhm.
else is going on. So I definitely understand why we see it as an error, especially.
Right. It's like, I just wanted that thing to work.
Yeah,
Yeah.
And now I can't continue. I mean,
Right.
that's the definition of an error right there in some ways.
Yeah.
I'm stuck. Now what?
But the flip side of that is you're not waiting forever.
Yeah.
So, because if you wait forever, you can't do any more work.
Is it worth considering that the timeouts are part of your like API specification at that point? Or is it still separate from that, but still related? I'm just trying to think of how to think of it properly.
So they are part of API specifications. For example, the TCP stack, which I keep coming back to, there are timeouts on connection, establishing a connection. There are timeouts on being able to read from the socket. There are timeouts on being able to write to the socket, and you can set those. They're part of the stack, and like at least internally inside your app. Like I don't know that there's, other than like maybe a document, a specification that says this operation will take up to this amount of time or fail. There's not really a way to say that that's part of your contract. And it's more about giving your consumers, like especially inside your app, like in a library or in some kind of like module that you build yourself, giving the things that call that function the opportunity to say, I don't want this to take longer than this amount of time. Or they, you just apply that, the timeout example snippet that I had wherever you need it. That's another possibility, is like spawn this thing into a separate process, wait, if that process doesn't finish in this amount of time, then give up and return a timeout error.
Yeah, now that I'm thinking about it, the timeout kind of is always on the client side in a sense.
Yes.
Right. If
Yes.
you're the one waiting for someone else to do something and get back to you. So it's in some ways almost the opposite of what the API specification would normally be, because the contract is, I give you something, you give me this back. In this case, they haven't given you anything back because you've timed
Right.
out.
Right. Yeah, and that's one thing I wanted to emphasize, but I didn't really figure out how to fit it in. Maybe the discussion, if I do this again, a discussion about buffering and queuing. The biggest danger with buffers and queues is disconnecting your consumers from the source of their problem. And in a sense, taking on responsibility for those consumers' behavior yourself. How to put that?
Synchronous, the RPC has a very nice feedback mechanism.
Yes, synchronous RPC has great feedback. The example I talked about in the podcast that just came out today, the Elixir Outlaws podcast with Amos, was a case, and Brian knows this well, where we just stuffed things into the Oban queue willy-nilly, and then our application was doing all this bogus work that didn't need to be done, and because we, like, anytime you put into that Oban queue, you're only dependent on the ability of the database to insert that row. Like, that's your only back pressure mechanism. It's not on how big is that table, how many jobs are ongoing. You would have to build that in yourself, or maybe Oban Pro does that for you. I don't know. But like, it's going to consume at whatever rate it can manage to consume at. But you can insert at any rate. And so these persistent things like brokers and you know, like Kafka is not really a broker, but people use it like that. They disconnect the producer from the consumer in a way that can be unhealthy. And so I always suggest, hey, maybe we can just do this with OTP before we try to ship it off into something that is like persistent and disconnected. And you know, those things are useful for sure. Like batch jobs are great for disconnecting the production of work with the consumption of it. But you typically do, like with batch jobs, you're trying to say, well, I need to do a batch job, which is going to process a ton of things. Not these one-off, like, hey, I kind of needed to do this thing async, so I'm going to put it on a queue. Instead of, you know,
Well, that's where,
thinking
like,
about processes.
async versus non-blocking becomes critical.
Yes.
That's a subtle difference.
I was thinking about queues. One of the other teams at PepsiCo just had a fun time because they do a lot of data refreshes on a queue,
Mm-hmm.
and then the queue stopped processing for a while, and it was a few hours before anybody noticed, and now they got like a few hours worth of stale requests to refresh over and over and over again, when only one of them they only needed one.
Yeah, it's a big risk that, like, things will sit in the queue too long, and then they'll no longer be relevant. And maybe you should have just dropped them and said, well, I know that there's another like refresh request coming,
Well,
so I'm just going to drop
now.
all these and then do that one, right?
Unfortunately, this was the school of hard knocks. With
Yeah.
I would say, but yeah, that's how it now is.
Yeah. So there's all sorts of situations like that you know, have made me be like, look with a very jaded eye at those sort of persistent message queue things.
It's kind of amazing how many people use Kafka as a message bus.
Right. Yep.
It's just that. Yep, I've seen it so many times. Just, I mean, because we use Kafka at Elixir report,
Mhm.
it's just the way people use it. It's like, that's not a good idea.
Well, it does kind of lend itself to that. In their defense.
It can. It's just,
It can quack like a duck.
yeah.
Yeah, and the protocol is really complicated, and especially on the Beam, the libraries are kind of a little sketch.
Yeah.
And maybe that's just because the protocol is complicated and the guarantees are complicated. But I also am like, do you really need that many trap exits in your code? No.
Cal Kingsbury recently did a write-up. He does the Jepson test suite. He recently did a write-up on Red Panda, which is like a drop-in replacement for Kafka, like it's API compliant. And it was really enlightening reading that, just him talking about kind of the inconsistencies in the specification for Kafka and some of the safety guarantees that I would not have expected to be there, that I guess were configurable not to be there, that were really interesting. So well, his entire, like all of his Jepson blog posts are very interesting, but that one in particular I recently read out, I really enjoyed.
Yeah,
I think you've
I
made
love
me think.
all this stuff.
I think you've made me realize that I might have misused Kafka at a previous point. Thankfully,
Hey, we've all done it.
thankfully, Kafka didn't let me do the thing I was trying to do with it, so we bailed to a much simpler like TCP connection. But I'm pretty sure, thinking back to that architecture.
Yeah, and I think also with the, I don't know if you all have followed this path too, but like, it can be easy to like hold on to that crutch of thinking about something that's asynchronous as a background job. Like if you came from Ruby or Python or something like that, and now you're doing Elixir, you know, the concurrency things available in those languages is just not, they're just not that sophisticated. And so you have to choose an infrastructural solution to the problem. And this is why I mentioned, like, you know, you're fighting, you might be fighting your language's concurrency model versus an Erlang Elixir. You know, you can do a lot of things ephemerally, and you're not going to hold up your main request path. You like, it's this, I hate to be reductive, as like as simple as spawn a process and watch it. Like with something, you don't have to watch it in the same process. You could put it under a supervisor and let that supervisor make sure it doesn't crash, and you know, stuff like that. But like it can be really tempting to pick that, you know, industry hardened piece of big software to solve your problem, and now you've got an ops problem when you could have just done it in OTP. So
I'll be honest. I know it would require a decent amount of code, but I never truly understand the use case of Oban in OTP.
Restarts.
Restarts is the big one.
The dashboard is really good for
Dashboard
being
is
able
nice.
to kind of able to introspect the kind of jobs and, you know, the number and whatnot. So like all the like niceties built into their dashboard can be really helpful. If, you know, but yeah, that's why I've really enjoyed using Oban in the past for that. And like if you're using a bunch of cron jobs, migrating from cron jobs to something on Oban is really good for, like, there's no telling how many people have had issues with, you know, you restart a server that's got a cron job on it and you're not entirely sure if you're going to like miss some sort of like scheduling demand or something like that. Oban, you know, takes care of that for you with the, well, as long as you're not like restarting or dropping the Postgres behind it. But yeah, there's I like Oban. I don't use it currently, but I have used it extensively in the past.
Yeah, and we've also, like Alan and I at Postmates, found it really useful for that cron type thing. Like we had, it's too bad Daniel isn't here, but he did most of the work on that, Daniel Flanagan. Just like slurping in all the menus from all the vendors in one like 90-minute period. Oban was great at that. The other thing is like work at distribution. If you're not using Distal and you don't like want to build those coordination primitives yourself, like Oban just kind of does it through the things that Postgres provides. And that's pretty nice. You don't have to think about it. But again, like, you know, the big problem being you're disconnecting the source of the work from the work being done in a very like asymmetric way. So you have to be careful about what you do with it.
What? Okay.
Go ahead, person.
It's Alan.
What are the like valid in your eyes use cases for Kafka? Because I'm sure, like we've said, I've certainly been guilty of using it probably in places I shouldn't have and regretted it. But what would be places where it would be ordained?
If
I
you're
would love to
using-
hear people that say that.
If you're a Java shop.
If you're a Java shop.
Okay, let's substitute in RabbitMQ and continue the conversation.
Okay. Well,
I
but
think if there's an, I mean, from my personal experience, if it's not basically using it as a background job library, it's, you've got some type of event that you need to handle and then propagate that out to other services that can then handle that event in the way they need to, but not necessarily just like doing work that one service is like saying, I need this work done. Other services, okay, I'll do the work that you have now put into this message.
Got it.
It's actually like a distributed system that says, hey, we need to do this specific thing with this event. There's another system that needs to do this specific thing with this event that's completely different from other systems.
Mhm.
How's that different than a topic though? Why wouldn't
Well-
a topic do the same thing?
But that is what a topic is.
Yeah. I think a different kind of use case that I think I might be using it for, I may or may not, for my architecture, which is I have to do, so I'm going to be sending out webhook requests to outgoing, and I want to put it all, I might put it all into a Kafka queue or thinking about it. And then if the person wanted to go back and look at what actually got sent, I could then
Mhm.
rewind the Kafka queue and look at it, just give them, here's the things you thought you were going to use. I was thinking about using it for that. I don't know if that's a valid use case or not.
Yeah, and especially if you need to be able to replay. Like
Yeah.
that's the big thing. You can rewind to the first event that's on the topic and retry things. And like that was the original use case at LinkedIn when they came up with Kafka was, every day we need to reprocess the social graph. So we're going to take all the things, all the data that we got about, somebody connected to this person and they connected to that person, and it's got to be processed by a lot of different systems. So we're going to put it all in one place, and every night they rewind and they like process through it and they build their data files for the next day and they stuff them in their, they were using Voldemort, a key value store for a lot of that, but like they could produce, I want to say it was like Parquet format or something, and just like toss it at Voldemort and it'll like swap out the files. But yeah, the big thing was being able to reprocess from the beginning. Or if you need to like spin up something new that does something new without that doesn't have the data already in the form it needs, it can like start up a new service from nothing and process the entire topic and then have its data set ready to go.
And Alan, the reason that when I see it used as a message bus at my place of work and say it's a bad idea is because Kafka just comes with a ton of complexity that you have to deal with, that there's other solutions for doing that stuff that you don't have to deal with that. The whole idempotency thing, what happens if you replay from the beginning? Like, are you going to have this huge set of data that's conflicting with your previous set? Like, there's like what happens when a partition gets stalled? Yeah, there's just like not blocking the header situations. There's just a lot of there that you're buying into when you're using it for simple tasks like that.
When a partition gets stalled, does that mean like, hold on, it's been like over a year since I've used Kafka, so I'm just give me a second.
Basically, it's just whatever's processing the partition for that topic on a consumer just basically can't make progress. And the partition then thinks, oh, the consumer's dead, and then it restarts and
Gotcha, yeah, okay.
reallocates it or whatnot. So.
I was just gonna make a comment about the talk before Alan interrupted me.
Sorry,
You had mentioned, or I believe you made the point that back pressure exists in the system, and so like timeouts not as an error, and like basically your entire talk was just talking about if you're having a conversation with someone who's like, oh, we have to deal with the back pressure, because a lot of systems you go in, you're doing low traffic, you don't think about a lot of these things until you get into higher traffic scenarios where you're more likely to run into these errors. The back pressure already exists in your system. It's just whether or not you define how to handle the situations or not. is kind of what talking about these tools is about. It's like, do you want to hit some unexpected, upper limit of some system and blow up, or do you want to define the things such that you can, say, here's the unhappy path. So that's something I took away from that I'm probably going to incorporate in conversations going forward. It's like the back pressure is already there. It's just whether or not you actually want to define how to handle it or not is kind of the question, what these tools help you do.
Yeah, I mean, you always have the option of load shedding if your server decides to give out in the middle of what it's processing, right?
Yeah, just drop. Don't fail. Just drop the work you're not going to do. Yep.
Let it crash.
Let it crash.
Was
Yeah.
it Delta
no,
that
no.
all their servers caught on fire? They had some back pressure there.
How often catch fire? Literally.
Like the data centers, maybe that was like a year or two. Oh, gosh, COVID messed up my historic timeline. This might have been like 4 years ago. I don't know. But Delta had like two, like their main data centers, like side by side. They caught on fire, and then they couldn't do flights for like 24 hours or something like that.
Mhm.
IBM was like, woohoo, Marsh beans.
Yeah.
Jordan, you were saying that was OVH?
OVH caught on fire
Okay.
a year or two ago. Maybe it's different. Maybe that wasn't the Delta thing though. So.
No, yeah, maybe that's what I'm thinking of.
See you, Jeremy. Have a good one, Jordan.
See you tomorrow.